Welcome back, everyone, to session 4 of the Gridlab-D developer training. Today's topic, we're going to cover testing and validation, which is actually quite an extensive topic. There's a lot of issues and details to cover for developers in particular. And as we'll see in the discussion today, validation in particular is a challenging problem for a tool like Gridlab-D. But before I get started with the main topic today, we had an exercise from last week. So what I'd like to do is go over the solution to that exercise. I think it covers a number of interesting details that tend to be overlooked when people develop models and tools for Gridlab-D, but these kinds of issues are important. And so this exercise was really designed to give us an opportunity to look at some of those questions. And if you recall, the exercise itself was to create a simulation that covered 1 month in Los Angeles with a schedule with a value that changed during the course of the week. And this is a really typical problem that we encounter in creating Gridlab-D models, where there are exogenous pieces of information that have to be introduced, and that information follows a particular pattern that's very repetitive. It might repeat on a daily basis or on a weekly basis, monthly, or even annually. And the mechanism for constructing that is called the schedule, and we talked about the schedule object last week. What this exercise does is it allows us to look at how a schedule gets put together. The other part of the exercise that's really interesting to look at and understand is how a filter works. And in this case, we're using a very simple delay filter. And then we're going to look at how the results of that are recorded in a CSV file. So what we're dealing with in this exercise are 3 important things. One is how to input information in a non-obvious way. Clearly, if we wanted to create a schedule, we could just create a player and just play the values in. But the convenient part about creating schedules, it allows us to design them in ways that match the way we think about a lot of the inputs in a tool like Gridlab-D, rather than creating a time series of values that we just put in. And then the filter really is an important aspect of how Gridlab-D works, because it allows us to think about how information flows through the simulator in ways that matches how we think about control and signal processing. And so this delay signal filter is an important example of how that's done. And then finally, recording data into a CSV file allows us to talk a little bit more about that process. So this particular exercise is fairly straightforward. And what you see on the left is the solution to that exercise. And so I want to highlight a few different things that come up. And some of them I'll actually emphasize again at the end of today's presentation, when I get into something that I hope to use a little bit more often, what I call the pro tips. The kinds of tricks that people who do this kind of work in Gridlab-D use repeatedly, because it's such an important or it's such a helpful kind of feature that we use it over and over again. So, all right, so let's get into the solution. Clearly, the first thing that's important to know is that we need to use the tape module, because we're going to be using a recorder, and the recorder is implemented in the tape module. And this feature of the tape module allows us to save the data in a format that's convenient to look at as a simple CSV file. What it does is it creates a header in the CSV file that contains the property name. So you can see over on the right side, the first line of the output of that file contains the timestamp and the 2 values that we're going to be creating. The next part is the clock. And so if you recall, the first feature that was called for in the exercise was to create a simulation in Los Angeles that runs from January 2022 to February 2020 through February 1st, 2022. So this is essentially setting up a 1-month simulation in Los Angeles. So notice I don't have to specify the time zone for Los Angeles. Just by specifying the country, state, and city, it knows what the time zone is and it sets the locality up correctly. The next part, and this is probably the most important feature that comes out of this exercise, is creating the schedule. And so in this case, you can see that the schedule syntax is designed to meet that 9 to 5 requirement for weekdays. So you notice here that the minutes are not specified. It's just all minutes, and neither is the month, the day of the month or the month of the year. So this applies for the entire year, but the weekdays are specified. 1 through 5 is Monday through Friday. So what this says is 9 to 5 Monday through Friday, the value is 1.0. And then 9 to 5 Saturdays, the value is 0.5. And if you recall, that was the requirement. And then for the remainder of the 9 through 5s that we haven't yet specified, which is Sunday and holidays, the value is 0. And then for all other days, the balance of the time is from 6 to 8 a.m. The value is 0 as well. And so what this does is this creates a full schedule, right? All the values have been specified. And that schedule can be then used as an input later to a value, and it will feed that value with this as the input. The next part of it is to create a class that has two properties, an X property and a Y property, where the X property is going to be the input from the schedule. And in this case, you can see down here that the way we've created the X property or defined it for this test object is it's just the input times 1 plus 0. So it's just copying the value through with a scalar of 1 and an offset of 0. And then the next part of this, of course, is creating the filter. And if you recall from last week's discussions, a delay filter is simply a 1 over z. If you, most people, I think, will remember that from their discrete time controls. And if you don't, it's a really easy thing to look up on the internet anyway. Wikipedia page has it. And so what we specified is a z domain filter with a 60-second update time. So the time step is 60 seconds. And so what this does is every 60 seconds, it will update the value that's targeted. In this case, it's the value y with the input x. And so we would expect that the value y will be equal to the input value x with a 1-minute delay. And then creating the recorder, we record both the x and y values. We save them to a file. And this interval -1 just means record the value whenever something changes. And so if you look at the output, you can see that the simulation starts with the value 0 at midnight, which is what we would expect. And at 9 a.m., the value x, which is the first column, is set to 1/2, which tells me that January 1st must be a Saturday, if I'm reading that correctly. Maybe that's something I should check, but it should be a Saturday. And then you'll notice that at 9:01, the value y is updated. So notice, you can see that the value of y is still 0 at 9 a.m., but because of the 1-minute time delay, it's updated to the value 1 at 9:01. And then, of course, at 6 p.m., the value of x changes to 0, so from 0.5 to 0. And then, but notice that the value y is still set to 0.5, and a minute later, the value y is updated. So you can see that the 1-minute delay is working correctly according to the specification of this filter. So this is a really good example of how all, sort of these pieces all come together in a fairly simple example, but you can imagine creating a much more sophisticated filter and getting sort of the response, for example, a demand response behavior with the delay, and maybe a second order demand response where it rebounds a little bit. Those kinds of things are relatively straightforward to construct using this kind of a mechanism. So before I go on, if anyone has any questions about this, please feel free to post them in the chat. And I think this is a pretty typical example that is also used for validation, because we know exactly what kind of output we would expect to see. And as we'll see in today's discussion, we can use this kind of a test to verify the functionality of the time zone mechanism, of the schedule mechanism, of the class definition mechanism, of the filter definition mechanism, and of course the filter implementation and the recorder. You can see that all of these elements, key elements that are found in this example, could be used as elements to test out various functionalities. I see we have a question under object test for X. Why do we need, so we don't need to multiply by 1.0 and add by 0. One thing I usually do, though, is I include it to make it unambiguous what I'm trying to do here. The parser is looking for a linear function, and there are cases I've found where leaving out portions of the linear function can make the parser unsure about what it is that it is expected to do, and it might get a syntax error or be unable to resolve what is intended. By creating a linear function, that makes it completely unambiguous that it's to take an input of some sort and scale it before applying it. Typically, I will leave out the offset of +0 if I don't use an offset, but I'll almost always include the scalar. The other thing that I find I do quite often is that I don't put constants in here, but instead I might put a scalar that does, for example, a load factor. So you might imagine that the schedule could define, for example, the peak load. And then you run a test at various loading levels. So you might run it at 1/2 peak, at 80% peak, at 100% peak, or 120% peak. And so then instead of using 1.0, you would use a global variable that would just scale the schedule accordingly. And you could apply this to values throughout the model. So this is just to give you a sense of what the general syntax is like, but you don't have to do that. And as I said, I think it's useful to know that you can apply global variables here to the calculation to do scaling for a range of studies, for example. Okay. All right, so let's jump in today to today's discussion, which is validation of agent-based simulations. So if you recall from our first session, Gridlab-D is an agent-based simulator. And because of that, it's not really typical in the way software that does engineering analysis works, in the sense that it's not simply applying an optimization or a ordinary differential equation algebraic solver, or even ordinary differential equation or differential algebraic equation solver for either steady state or transient dynamic simulations, where essentially if we give a set of inputs, we know that we're going to get, we must get a set of outputs that are, clearly known in advance. We know what the right answer should be. There are many cases in Gridlab-D where the behavior of the simulator uses something called emergent behavior. So the outputs might be rather difficult to examine. There might be a lot of outputs, and there may not be an obvious solution because of random numbers that are involved in generating the outputs. There are ways to make the random number generators deterministic, and that helps generally with some of that effect. But in many cases, we don't actually have an exact solution available from another tool that we can compare against. Gridlab-D is quite unique in many of its features and its behaviors, and so there really isn't another tool that we can run that has the emergent behavior that we would expect to produce the same result in every case. So that's a tricky problem, and generally what we found working with Gridlab-D is we have to use some workarounds to avoid situations where the emergent behavior becomes the dominant feature of the output that we're looking at. So one way to do this is to simply validate individual agent behaviors when we give them scenarios that are clearly known. So for example, if I give a house model a certain weather data for a certain physical setup of the house, then if I turn off all the random number generation in the house, I should get pretty consistent behavior out of it. And if it's set up, if the validation test is set up correctly, I should always get the exact same behavior. And so it's possible to set up scenarios that verify many of the features of a single agent, single object in Gridlab-D, and get always the same answer. So that's one way of dealing with this kind of situation. Another way of dealing with it is to create Monte Carlo studies where you generate a lot of different scenarios, a lot of different runs with the same scenario, knowing that the random number generators should produce results that the output should fit in an ensemble which has the statistical characteristics which you expect. And so some of the tests in Gridlab-D do that, particularly tests of the random number generators, where the distributions should be of known characteristics, so that we can verify that, for example, a normal distribution produces the expected mean and variance for a large sample. And then, of course, that can be extended to larger studies. So, for example, you could generate a distribution of houses, and then you would expect to see a distribution of energy consumptions that correspond. And so that is generally how we deal with those kinds of challenges. But it's not, there are no hard and fast rules about the right way to do things. And so it's just something that you, as a Gridlab-D developer and model creator, you kind of get the hang of. But basically you just have to use good engineering judgment and work from examples that are already in existence, and try to make variations that address the kinds of problems that you're trying to validate. So that's just a general background on the validation challenges for Gridlab-D. To test Gridlab-D, there are basically two basic mechanisms available to you. The first is to test the internals of the core engine itself. There are a whole lot of subcomponents within the core that provide all sorts of capabilities, and we have test mechanisms for all of those. We don't run all of those tests all the time. Basically, we just run them whenever we change something in a particular part of the subsystem, and for the most part, we don't need to rerun those tests. There are also tests built in for Python as well, and we'll talk about using the Python unit test module to verify all the subcommands and tools that are built on Python itself. And then there are the Gridlab-D validation tests, and those are a large number of Gridlab-D models that have been developed over the years, mostly by PNNL, to verify all the ranges of functionality that need to be supported by the GLM syntax itself and the modules that are loaded when people are working in different domains. And so this runs through a very wide range of tests. And those tests are used to check things like, whether we handle errors and failures correctly, whether the syntax in the GLM syntax works correctly, and whether the outputs of modules meet the expectations. Generally, the way that's done is either through what are called asserts, and we'll talk about static tests in a minute, or comparing output files to a saved output file with known good values, and we'll talk about dynamic tests as well. So those are the basically the two mechanisms that are available to us for validating and testing Gridlab-D overall. So let me first talk about the core tests. Those are done from the command line, and they check some of the key components of the Gridlab-D core itself. And basically, the idea is to run a series of queries or calls to the functions internally to verify that the answers that come out of the actual code that implements those features meet the specification. So for example, the daylight savings tests, this first one, basically checks to see that daylight savings time changes on the days when it is expected to change. And so it will do things like testing the week before on Sunday, the day before, the day of, and a day after, and the week after, to make sure that the daylight savings time changes at the exact time it's supposed to change for a given year. And if you recall, in Gridlab-D, the simulator is actually aware of the daylight savings times rules at various locations in time zones and for various years. For example, the daylight savings times rules in North America changed last in 2006. And so that change should be verifiable, and this test does that. The next two end use and load shape tests just verify that the end use object and load property, the end use property and the load shape properties exhibit the correct behaviors for known cases. The lock test verifies that the memory locking system works correctly. And the mod test basically just does a module test if the module even implements self-tests of its own internal functions. As far as I know, most modules do not implement these kinds of internal self-tests. The feature is available, but most module implementers pass on doing that and instead do extensive tests using the validation command line, which we'll talk about next. The random number generator test just verifies that the random number generators exhibit the right aggregate properties when you generate a large number. Does it generate the correct mean, the correct variance, and so on. The schedule test verifies the schedule subsystem, very much like the end use and load shape tests. And then finally, the units test verifies the internal unit converter and makes sure that it does all the unit conversions as expected. If any of these tests fail, it outputs a test file, test.txt, which you can look at. It will tell you exactly what happened, which tests failed. As a general rule, if the tests fail, that means somebody has to go in and investigate why it is failing and address the failure. One thing I should note is that on some systems, some of these tests are not expected to work. For example, memory locking may not work on systems that don't support the hardware memory locking that's required to allow parallelism. And if those tests fail, then parallelism, at least at the granular level inside the simulator, won't work. It's essentially, well, it shouldn't be used. So those kinds of tests can be informative about what kinds of features work on which systems and what we might expect from the validation tests. So here's an example of running a units test. And so the output of the test file just verifies what the test was, and then outputs all of the individual tests made. This is just the first few tests. There are hundreds of tests that are implemented. And it's just testing obvious things like unit equivalences and so on and so forth. It also allows us to verify syntax and things that might be important for people to define their own custom units as well. Okay, so the next important testing mechanism that's available is the unit testing module in Python. So whenever a Python module is implemented in Gridlab-D, it has to be tested out. A test rig is usually you can implement your own test rig, but we really recommend using the Python unit test module. It provides sort of the best kind of feature set that people would need. And it's a good framework for conducting these kinds of tests and ensuring that a Python module works correctly. It does depend on the developer knowing what to test. So the choice of which function calls to test is really up to the developers. One approach is to just do high-level tests based on the specification. The entry point, here are the features that are supported, check each of the features, and that in principle should test all the pathways. Another approach is to test the individual functions themselves and make sure that each function meets its specifications. And then in principle, if all the functions do what they're told correctly, then the top level functions should work correctly. And you really only need to do a comprehensive test of the inputs and outputs. So the general approach is just to check that you're running in the main module. In other words, the module is being loaded as a script. That's how we typically conduct the tests. If you load a module in Python using the import command, it does not run this part of the code. This is only run when you load the code as a script, and then that script will run the validation tests. The only issue with doing it this way is that if you're creating a script, then that won't work because this test is already being used to decide how to parse the command line options. So the solution is to simply create a command line option for validate, and typically in Gridlab-D, that's just the -- validate command line option. This is really only an issue for subcommands and tools. So if you're creating a subcommand or a tool, then this sort of standard unit test mechanism isn't going to work, and you'll have to create a command line option to conduct the unit test instead. So that's just a caveat. It's not a major thing, but something that you occasionally run into. If you forget, it'll become noticeable rather quickly when the Python code is validated. Your script will not quite work as expected. All right, so general testing guidelines for the unit tests. Basically, you want to check all the endpoints that are supposed to be implemented. If it's a module, all the entry points for the module. If it's an API of some kind, all the entry points and endpoints for the API. In addition, you want to test all the internal functions and make sure that they work as they're supposed to. This can be incredibly tedious to put together if it wasn't done by the developer who created those functions, but it is something that really should be done. My suggestion would be, if you're a developer and you're writing the code, write the unit tests at the same time. If you do the two together, it makes your life a whole lot easier in the end. The end product will be quite a bit more, it'll be quite a bit easier for others to incorporate into Gridlab-D when you hand your code off to be in a pull request to be incorporated into the main body of code. The next is to do failure testing. So you want to verify that when you pass invalid calls or invalid features, that the code fails as expected, either through a return value that is picked up or through an exception. And then you also want to do bounds checking. So verify that your inputs, when they go out of the acceptable range, that the system, the function handles that correctly. And of course, that the outputs are also within the acceptable range of values. If you do these four things at a minimum, your code is very likely to work consistently, and you'll catch situations that emerge either because a library changed or some specification changed. Those things will be much easier to catch later on. So if you follow these guidelines, it's just good practice, and it helps others work with your code later on. All right, so now we get into the real meat of the validation system in Gridlab-D. Gridlab-D has a very extensive validation framework that was developed over the years based on experience, initially at PNNL, but then coming from others over the as modules were added over time. And the validation framework is based on primarily on the Gridlab-D modeling language, the GLM file. So obviously its primary function is to verify that the syntax of the files is correct, that the parser is working correctly, that the loader, all the loader options work correctly. In addition, it verifies that all of the macros that are used to run subcommands, to manipulate geodata, to use the tools, that all of those also work correctly. One of the biggest uses of the validation framework is to verify that static models solve problems exactly as expected. And primary among these, of course, is the power flow solver, the building thermal models solutions, the market model solutions, the climate data handling, all of the things that where you basically are retrieving data and doing a calculation and verifying that the output matches an expected value. And so those kinds of static checks don't require a clock. In fact, clocks can make those checks a lot more difficult to do. It is possible, but generally clocks are not involved. And if they are, the static check is done at an instant in time, and we'll see how that's done. Dynamic model checks are models where the clock does run, and so the output is a time series. And in that case, the verification of the output with a known good output that was previously obtained is done using a different mechanism rather than asserting that a value matches. The final kind of test is a parallelism test. We don't do a lot of those tests directly in Gridlab-D, but if you do your validation tests, particularly if you do a comprehensive validation test at Gridlab-D, you might notice that it takes a long time. So one of the things that most of us do is that we run those tests in parallel. And of course, that gives us the parallelism check as well. It verifies that Gridlab-D can run concurrent runs without having the runs interfere with each other, and sharing the resources on the system in a productive manner without causing all sorts of parallelism problems that might arise if things were not implemented correctly. So those parallelism checks are not directly implemented as part of the validation suite, but they are done almost every day by developers. And so we typically do catch problems of parallelism fairly quickly. So let me go through the basic features of how the validate command line option works. And so essentially, if you do the command gridlab-d-validate, this will test everything in the Gridlab-D tree, source tree. What it does is it seeks out all folders by the name of autotest, and it scans those folders for files that have a particular pattern. So that pattern can be, it has to be a file that starts with the word test underscore and ends with the extension .glm. Everything in between is allowed, but there are specific patterns that have some important features. If the pattern includes underscore ERR, then rather than the test having to succeed, the test must actually fail. This allows us to create tests that verify that failures that we expect do in fact occur. So you think about, we can have tests where we expect a value to be, or a simulation to succeed, and so the test must pass. The simulation must succeed in order for the test to pass. We can also have tests that must fail. The simulation must fail in order for the test to pass. I know that can sound a little confusing, particularly if I don't say it clearly. But again, the important thing to understand is the simulation for this first case, the simulation must exit with an OK for the test to pass. And in the second case, the simulation must exit with a failure in order for the test to pass. In addition, the pattern underscore OPT just means it's optional. And so those files are ignored. They're not even run. And these can be used in as support files that are inputs to other simulation tests. And it allows us to organize the files in a nice way the other thing that happens a lot is when tests don't work the way we expect, people will rename them as optional until we can figure out why they don't work as expected without causing the rest of the infrastructure to fail. Okay, so a couple of useful options. The -W option allows us to scan only folders within the list. So for example, if we say -W module power flow, then what it does is it only scans for the Autotest folder within the power flow module. So that limits the test to only those files, and the test would go a lot quicker. What that's really useful for is if you're making changes only in one particular section of the code and you want to make sure that you didn't have any effect and you don't want to wait for a full test suite. This allows you to just run a quick test of that module alone. The other useful feature is what I mentioned earlier about parallelism. If you use the -T option and the number of processors, you can run a parallel test where it will use the specified number of processors and essentially allow you to run multiple simulations concurrently. If you specify 0 as the number of processors, it will use as many as are available on your system. So if your system has, for example, 16 processors on it, then it will be the same as saying -T16. So if you don't know how many there are, or you don't really particularly care to run a specified number, then you can just say -T0 and it will run a maximally parallel simulation validation sequence. Another important thing to understand about the validate command line option is any other options you specify before validate will be applied to the Gridlab-D instance that's doing the validation. But any options you specify after the validate command line option will be applied only to the simulations that are run by the validation process. They will not apply to the validation Gridlab-D instance itself. This seems like a pretty obscure little feature, but if you think about it, the -T proc option really only applies to the validation sequence. We don't want it to apply to the each individual simulation. We want each individual simulation to use only one processor, the one it is assigned. And so that kind of feature is important to understand. If, for example, I wanted to run each validation test as a parallel simulation, then I would put the -T proc afterwards, and it would tell each simulation to use so many processors. So for example, if I had 16 processors, I could run 4 validations in parallel, each of which has 4 processors. So I would put -T proc 4, -T4 validate -T4, and then that would give me 4 validation runs, each with 4 processors. So that's an important thing to understand about the validation command line option. Here's a output from a validation test. In this case, it's a parallel validation test. It looks like it's a full test, but you can see that the test resulted in 2 errors, one exception and one in an unexpected error code. In other words, this test was not expected to give an error. It had to pass. It had to exit with successfully in order for the test to pass. So the test failed because the exit code was not 0. And in this case, the test never even ran. Something else happened. And in fact, it's telling us here there was a process control problem. And so those 2 failures are then reported in the validation sequence, one as an unexpected error and one as an unexpected exception. And so of the 721 tests run, 719 of them were successful, which is a 99%, better than 99% success rate, almost 100%, but not quite. And the other thing is it tells you what the total runtime for the test sequence was. So here it's a little bit more than 2 minutes, which is pretty good for a parallel process. Notice that it was run as a parallel, use as many as you can process. If it had been a sequential one, it would have been significantly longer. My guess is probably on the order of 10 minutes. So you can see where the parallelism does have a significant impact. on the total runtime. And then because it was a failed validation, we probably want to inspect the validation output. And I've removed all of the successful ones here from the output of test results, but you can see the exception is listed and the error is listed, where the first letter identifies which type of error was encountered, and identifies which file it was and how much time elapsed time was used before it detected the error. And then it gives an overall summary of the test result. And then in the header for that test, you can just see the general features of the test request, just letting you know which options were used. This is for the really for the developers to help identify if there are any problems with the test system itself. Generally, this is not too important to us as developers who are validating the code that we've been modifying over time. So yeah, that's basically the way the validation test sequence works. When you're inspecting test results, you need to basically go and look at the output itself from the simulation. So what I'll do here is kind of go through what happens and how things work. So here's an example of the test that we saw earlier in the previous validation example. So you'll notice that we're testing a file that was found called testmediostat.glm in the tools autotest folder. And so the way that works is it creates a folder by the same root name. It removes the .glm, and then it copies the GLM file into that folder, and then runs Gridlab-D on that file, and the outputs are then generated into that folder. So that's the basic mechanism. And so if we detect an error, then we basically just need to inspect the appropriate output file that was generated. In this case, the gridlabd.err file contains the exact cause of the error. And in this case, it looks like it's testing the exit on exit 0. So the exit condition successfully ran the simulation and is now comparing the output file, and it notices that the files are different. And so what that's saying is that the test that I ran generated an output that was not the same as the original output that was expected. And that's considered a test failure for this class of test. This is typical of a time series output where we anticipate a certain series of values and of course we get a different one. All right, so let me now go through a little bit more detail in how to implement static and dynamic tests. So here's a simple example of a static test. This uses the assert module. Assert module tests use assert objects. And in this case, I just created a simple class with the value x. I assigned the value x the value, I assigned 5 to the property x. And this assert test just verifies that x is equal to 5. So obviously this should pass, right? X is equal to 5 if everything works in the system. And of course, if x were slightly different from 5, but I wanted to verify that it was close, then I would use a variation. So here's an example of the same kind of test where the value x is slightly different from 5, and I'm comparing to the value 5 within 0.1. So in principle, this test should also pass. But if I had a value, say, of 4.85, then it would not pass. So this is just a simple example of how to use the assert property to verify that a value meets a particular characteristic. So let me go through how asserts work generally. You should always specify the target, and if the target has parts like a complex number has real or imaginary, magnitude or angle, and an end use might have other properties. Some properties have parts, and you can then specify those as well. But in general, if you're just looking at the target itself, you'll see the underlying double value that you are comparing against, or if it's a string, you'd be comparing against a string value, and you wouldn't have range checks and things like that. In general, you can specify the typical relations you would expect. And those relations can be verified, as you saw in the example before, to match a value or be within a particular value. There's also the inside and outside range, but those are now compared against the lower and upper properties of the assert object rather than value and within. So that allows you to do a check whether the property is inside or outside of a range that you would expect, without having to specify the mid-range or a within range. You can also use the start and stop values to specify when to apply the assert object itself. So these are timestamps. So you can say that the property needs to be verified only when the clock is within the range of that timestamp. If you don't specify start, it's assumed to be the initialization of the simulation. And if you don't specify stop, it's assumed to be the end or never, the end of the simulation. So you don't have to specify both. You can specify just one. And if you specify just start, it will be from that point on until the end of the simulation. If you specify stop, it will be up to that point. Another property is whether the assert has to remain in effect, remain true for a certain amount of time. So you can specify the duration that the assert has to be true using the hold property of the assert. And then finally, you can specify a group over which the property over which the assert is applied. So that refers to the object's group ID. That allows you to restrict the check to only properties that meet that particular group. That means you don't have to make the property parent set to anything in particular. Otherwise, the assert only applies to the parent object. And that allows you, of course, to embed it within an object. But if you don't embed it in an object and you use group, that means it will apply to a whole set of objects. A couple of caveats on assert. Not all tests make sense or are unambiguous when you implement them using asserts. And so if you run into a situation where the assert doesn't work the way you expect, then it's a good idea to use a type-specific assert. And so there are 4 type-specific asserts that have been implemented in the assert module. One that's specifically designed for doubles, one that's specifically designed for complex values, one that's designed for enumerations, and one that's designed for integers. And those will get around sort of the quirks and ambiguities that sometimes come up when you're using the general assert, and the comparisons don't work as you would expect. It's not really common that you run into this problem, but when you do, these asserts are more straightforward to implement and don't run into those kinds of odd ambiguities about how things get compared. All right. So as a general rule, static models and static validation does not use a clock. In other words, it's basically a one-shot solution. The model is loaded, it's initialized, it's solved, and the simulation stops. You can turn a static simulation into a dynamic one by simply adding a clock. And generally that will result in the simulation clock advancing, and as a result, the object's behavior most likely changing. Sometimes there are characteristics of a model that will cause one shot to advance the clock anyway. And so the solution to that is either to specify the -I option on the command line, which tells the simulator to only initialize, or to specify the clock so that the start and stop time are the same, and that causes it to essentially not advance. Some good examples of things that cause the clock to advance are schedules. If you have a schedule, the clock may advance. Players may cause the clock to advance depending on what kind of property they're affecting and whether that property will affect the object's that use those properties. One thing that's subtle and occurs quite often in power flow models is controls on devices. So if regulators and capacitors and those kinds of objects have controls enabled rather than set to manual, then those devices may cause the clock to advance because they will notice that the solution does not meet the control objective, and so they will change the settings, and that will cause the power flow solver to advance the clock. And so you'll see that the simulation may advance the clock a little bit until the controls stabilize. It's not necessarily something that you want, and the way to avoid that is to set those controls to manual. So yeah, any object which basically causes the properties to change over time will cause the clock to advance. And then of course, recorders will cause the clock to advance. That's in fact the point of a recorder. So if you set up a recorder to sample an object periodically, then the clock will advance to assure that the object gets sampled periodically. And so that's not an unexpected outcome. But if you're trying to create a static model and it includes a recorder, you'll have to be careful about making sure that the recorder doesn't push the clock forward, because then you won't get that one-shot solution you're looking for unless you specify the clock range that you want the one-shot solution to be over. So that's just things to keep in mind. Of course, the flip side of that is if you want to turn a dynamic model, a static model into a dynamic model, doing any of these things will do it. Will cause it to become a dynamic model, and it will cause the clock to advance over time. If the clock starts to advance and you don't specify a stop time, it's quite possible that the solution will never reach steady state, and the clock will advance until the end of time. And in Gridlab-D, the end of time is, I think, 1,000 years. So depending on the complexity of your model, it could take a while to complete that simulation. And so it's generally a good idea, if you're turning a model into a dynamic simulation, to just go ahead and specify the start and stop times to make sure that the clock runs over the time range that you anticipate needing a solution. Otherwise, it's hard to say when it will run until. It depends on your model, and it'll typically start at the default time, which is, I believe, January 1st, 2000, unless there's something in the data that causes it to start at some later time. All right, so in order to create a validation test from a dynamic model, the best approach is to simply generate an output file and then compare that output file to a known good output file that has been previously generated or obtained from another source. And so essentially what this amounts to is creating an output file in the Autotest folder itself that will then later be used as a comparison. So when the simulation exits, then the test folder itself should contain that output file again. We have a question here. If the start time is equal to the stop time, is the model still static? Yes, essentially. It should start and it should immediately stop. That would be equivalent to specifying the -I option, except that it runs one extra solution to make sure that everything is synced and committed. Okay. So yeah, when the dynamic simulation runs, the clock is advanced and the output is generated to this output file in the test folder, and then we can compare the two. And so the trick here is to place an output recorder that generates the output file that we're looking for, and then to check to see whether the output file exists in the original input folder, and then just run on exit. If a successful simulation is completed, just do the difference and run the diff command. And if that difference is non-trivial, then this on exit command will fail, and the difference will be stored in a file that we can then inspect. I will get to, so another question is, when you compare CSV to a known good, do you mean from another simulation? It could be from another simulation. It could be from a validation that was run previously by the developer. So basically to detect a change in the output since the last time it was run. And in fact, I'll show you a way of doing that automatically so that we can verify whether output has changed from what the developer believes the output should be. So yeah, you can get that output file from either another source or from a previously run simulation of Gridlab-D. And so I'll talk about that in an example a little bit later. Okay, so here are some examples of looking at the output from a validation sequence on GitHub Actions. So you'll recognize here the Gridlab-D repository, and you can see we're looking at the Actions tab for that repository, and you can see here the this is the developer test to make sure that the developer branch is ready to be released into master, and it's failing. And so the result of that failure can be inspected. So if we click on this, what we see is the output from that test, and down here is the validation result that I was talking about earlier. And that validation result can be downloaded, and then the download can be opened up. And if you double click on the validate.tar.gz file, you get the contents of the failure. And this is actually the failure that we saw earlier. And if we inspect the gridlabd.err file, we can see that the difference is reporting that it failed. And so there's a couple issues here a couple things I want to bring up. So first of all, you'll notice here that there's a little extra option. Wow. Okay, hold on. All right. There's a little extra option. This is the diff option to ignore lines that start with comment characters. A lot of Gridlab-D tools will output a comment at the top of the file indicating how that file was generated. And of course, it includes a date stamp, and that date stamp needs to be ignored. And so telling diff to ignore the comments is a useful way of avoiding that problem. So the other thing that's important here is that you'll notice that it does not save the difference into a gridlabd.diff file. So whoever implemented it, and confession, it was me probably, implemented this test, forgot to put the redirection of the output to gridlabd.diff. And you'll notice that it's not listed here in the file, in the folder. That means that it went to the output. So if we go and we inspect the output, you can see here are the differences. That's not a friendly thing to do. This output should have been saved in the diff file, not to the standard out that is generated in the actions validation outputs itself. And so that's not a great thing, but we can see that what's happened is that the Mediostat tool is generating different data for these particular samples than it was before. So the last time it was ran by the developers and saved into that test mediostat.csv file, these values were different. And that is unusual and unexpected, but it's not unavoidable. The Mediostat tool is going out to an internet resource and collecting data, and every once in a while the implementations of those resources change a little bit. And so what we're detecting here is a change in the Mediostat API, and presumably that is intentional. That's something that they intended. It's not something that we would necessarily be too happy about, but it's not unexpected, I guess, from internet resources. And so this does happen every once in a while. So the direct answer to the question about how you save this file is a trick that we use for generating the data that we want. And so this is the trick used for input, but you can also use it for output. And I'll show you, I think it's either an exercise or an example later, where we're going to do something similar. So here's an example where the input data that we want, we need to read the input from the parent folder. So if you recall, the Gridlab-D model, the GLM files copied into the Autotest folder, but we don't know what the input files are. And so here's an example of reading the input file from the parent folder when it exists in the parent folder. So all we're doing is we're saying, if you find the input file in the parent folder, then we just set the source folder, and then it allows us to specify that when we're running in the parent folder, we use dot because source is not set. And when we're running in the Autotest folder, we use dot dot because we found that file in the Autotest folder. So this is what we do for inputs, but it is also the same thing that we would do for outputs. When we detect that we're running in the Autotest folder, we would generate the output using a recorder and going out to the, doing a similar thing, going out to the folder that we want to compare the output to. Okay, another issue is parallelism. So a lot of Gridlab-D tools and subcommands access data files that are stored in a shared folder or cached folder. And so any command which manipulates those files should be working with the, in a way that is sharing safe. So for example, if you're copying a file from the internet and you're copying it to the cache, you should use the subcommand or the tool that does that rather than doing it yourself. Otherwise, you will likely have to implement locking yourself, and that's tedious and not fun. Another important thing is don't use any shared temporary folders. You should be creating a unique temporary folder that belongs to only that simulation, and you should clean it up afterwards. So that kind of issue comes up fairly often when you're doing large complex simulations. One thing to do is just keep all your files in subfolders within the folder that you're running, and then you're safe, because the presumption is that no one else is reading that folder at the same time as you are. Another big issue or caveat is that some commands, some subcommands and some tools require credentials. You should absolutely never store your credentials in any of the test files. This will get caught by GitHub, and it might get caught by whoever, whichever API is actually using those credentials, and cause all sorts of problems. Not to mention that it would allow people to use our systems, your systems, for their own nefarious purposes. There are mechanisms in GitHub for implementing secrets. I'm not going to go into the details of how to do that. If you do run into a situation where you need to do that, there are help resources on GitHub and elsewhere for how to implement secrets and credentials in validation tests. It's not a most straightforward thing to do. And so generally what we try to do is make copies of the key files that are needed to test systems where normally credentials are required, and we'll use those copies in order for validation tests. If we're trying to validate the credential mechanism itself, that's a separate issue, and of course that would require that you implement GitHub secrets. The other thing that we strongly recommend is that you not use HTTP whenever it's possible, and instead use HTTPS. That does provide some measure of security in the retrieval of files from remote resources. The other thing we've noticed is that sometimes tests that involve internet resources will fail, either because the resource was too slow or rate limits were encountered. That's not unusual. If that happens, wait a little while and try the test again. Usually it passes. That's not the most ideal thing for testing frameworks, but it's somewhat unavoidable when we have so much stuff coming from the internet. All right, so now I want to jump into discussions of the static load models that we use. Some of these static load models are also used for dynamic load, dynamic tests. But in the case of power flow simulations, These models are really crucial to verifying that everything in Gridlab-D works correctly for power systems modeling in particular. So the feeder models that are available for anyone who wants to do a test are in the Gridlab-D models folder. We recently restructured the folder to clean up a little bit the way things are delivered. And so all of the HiPAS models that are needed for static testing are in the Gridlab-D 4 folder. All of the older models that were developed at PNNL are in the Gridlab-D 3 folder. And that folder has been largely left in the state that it was in after we downloaded everything from the original source code at Slack and did all of our development over the last few years. So there's a lot of stuff in there. We're going to do some housekeeping on that on the Gridlab-D folder over the next few months, but the Gridlab-D 4 folder is pretty well structured the way it should be for validation and testing purposes for the HiPAS version of Gridlab-D. One of the things that we've done in all of these models is ensured that all the controls for all the devices are set to manual so that the models are indeed static solutions. So if you just load the GLM file, it will solve it, and that's it. It won't do anything else. The clock should not advance. If it does, that's a problem, and please let us know and we'll correct it. So in addition to these IEEE models, the 13, 37, 123, 342, and 8500 bus models, we also have some models from PG&E that were developed under a project that CEC funded some years ago. These are PG&E taxonomy feeder models that were used for a PV study. Those models have also been readied for validation of HiPAS Gridlab-D. And in addition, we have the US taxonomy feeder models that were developed as part of the Modern Grid Initiative, and I'll go into some details about those, about 25 feeder models that are representative of a national sampling of feeder models from North America for a variety of different feeder types and structures serving different communities, different size models, different voltage levels, different settings for the types of loads on those models. And so this range of models really gives us a pretty broad sampling of the kinds of load models and network models that we would expect to see. So first, let me talk a little bit about the IEEE 123 models. We are still working on the validation of all these models, but here's an example of the 123 feeder model solved, and then the voltage profiles output to verify that the model is working correctly. Typically, the solutions match pretty well with the expected solutions, and the original P&L versions of these had the exact voltages that were calculated at specific points as asserts. This model does not have any of that. It's a bare network model with the load model as stated in the original P&L implementation of the 123 solution. And so we would expect this model to always generate the same solution, and so a validation test that it produces the same answer would always be an appropriate quick check of the solver. So we could do this with the 13, 37, and all the other models. I'm not going to show those results in part because some of them appear to not be plotting correctly on the voltage profile, and others appear to not be solving as expected, but that's all stuff that we anticipate having resolved by the time we release in September. Here's an example of one of the PG&E feeder models. And so the PG&E feeder taxonomy models were generated around 2015, I believe, from a CEC project that was started now more than 10 years ago. These models are stored at peak load. So they really represent a pretty extreme condition on the feeder. we can change that, and we probably will make that a model that allows you to change the peak load or reduce it using a factor on the loading itself. That's not something that's currently in the model, but it's something I think that will probably be added here at some point in the near future. The other feature of these models is that all of the PV has been connected at the end of the feeder. So again, it represents kind of a worst case scenario for the feeder. And you can see this particular feeder, you can see that the voltage rises significantly at the end of the two phases. But the third phase doesn't have that characteristic. It has the sort of the normal, as you would expect, voltage drop. The only exception to that is this one feeder that has a distributed PV on it. And so it has a more sort of typical characteristic of a heavily loaded feeder with PV running throughout the feeder itself. But otherwise, these models all run fine and produce the results as expected. Let me go into the taxonomy feeders in some more detail. These are important feeder models that we use for testing Gridlab-D and verifying the solutions. There are a total of 25 feeders. They were developed using a sampling, a clustering mechanism based on feeders that were collected from utilities around the United States. These were clustered according to climate regions, voltage characteristics of the primary voltage on the feeder itself, and then there was a feeder ID assigned to uniquely distinguish between each of the feeders within each region. So in region 1, that's the Pacific Coast area, and we had 129 feeders that were used to generate the sample of, I believe, 5 or so feeders. And then the same thing was done for region 2, which is the northern part of the United States, region 3, the desert southwest, region 4, the mid-Atlantic kind of subtropical climate, and then region 5, the tropical climate of the Gulf states. And so if we look at these, each of these regions, what we see is that there's a variety of feeders. In this case, this Pacific temperate climate region has 4 12 kV-ish and 1 25 kV model with a variety of peak loading conditions and a variety of nodes. And these represent different kinds of urban, suburban, and rural mixes in the loads themselves. And so similarly, in the northern region, we have a breakdown of different voltages, including a 35 kV network model. That's pretty large. That represents a very light rural loading, and you can see the other kinds of load mixes that are available for the other feeders. For the desert southwest region, we have again just 3 models, but one of them is a very large model with a heavy suburban loading condition, and the others are just representative of moderate urban and heavy urban loading. In the mid-Atlantic subtropical climate, again, only 3 models, but here we see a variety of voltages being used, including a high voltage, light rural system that has a fairly small model. And then finally, the tropical climate for the Gulf states has a wide variety of systems, and we see a variety of loading conditions and variety of voltages and system sizes. So running all of these different models allows us to test Gridlab-D in a wide variety of loading conditions and system network designs that we would find throughout the United States. And this is really allows us to not only test the simulations in a wide variety of conditions, but we can use these models to extrapolate results. And as we'll see in later sessions, that ability to extrapolate across from a local solution to a national level is a useful capability that's available to us. So I just want to sort of wrap up this part of the discussion with an invitation for anyone who works with Gridlab-D to submit models for contributions. So if you have models that don't include sensitive information, they've been sanitized of customer data, they have aggregated loads, the identifiers, for example, the geographic information have been removed, then those are models that may be very well suited to be part of the Gridlab-D models, static Gridlab-D models that we can use for testing and developing validations for various applications. So we welcome those contributions. We obviously welcome dynamic models as well, but given how easy it is typically to convert a static model into a dynamic model, the preference is that we get static models. It can be a little trickier to convert a dynamic model back into a static model, although not that hard. So both are generally welcome. Sort of by way of broadening the invitation, it's not just power flow models that we are looking for. We also are looking for models that would help us study market modules like transactive system models, models that include loads, detailed load models like houses and apartment buildings, or offices and commercial EV charging parking lots, or even models of individual industrial facilities for which we do not yet have models given the NIAX codes. And then finally, we're always looking for models of equipment that are used in resilience analysis, like pole models, equipment model, vegetation, and so on. So if you have any kind of information that fits sort of those general categories, please feel free to submit them for review, and we'll put a pull request in for that, and get them incorporated into our test suite. Just to help cover the broad range of topics, as you may recall, Gridlab-D includes a template, a capability that allows us to deliver analyses from a templates repository. Analyses in the templates repository include additional Python and GLM code that are specifically designed to address a particular analysis need or capability that people generally use. And so those templates in the test repository, in the template repository, include tests as well. Those tests depend on the Gridlab-D modules repository. If you look at the template repository, you'll find that there's a makefile in there, and the only thing the makefile does is validate the templates. And so validation is basically done on the master branch and the develop branch automatically by GitHub. And of course, any pull request that's going to develop will also be validated based on the validation tests within the template repository itself. So the way this is done is, if you look at the template structure, right, these are the templates for the United States, California, and the Slack implementation, which will become the HiPAS standard templates. You can see that any use case that we have has a template associated with it. And so this is the integration capacity analysis use case. If you create an auto test folder in there, and you create a corresponding test folder that matches the auto test models folder. So if you look at, this is a copy of the Gridlab-D models repository. That copy, if you use the same folder, so you notice here the auto test models Gridlab-D 4 IEEE 13 matches the auto test models Gridlab-D 4 IEEE 13 GLM right here. If you create that folder, these files here will be copied to a test folder along with this 13 GLM, and they will be compared. So the output of running 13 GLM in this folder will then be compared against the output of or the expected output that's stored here. So the way this works is every file named autotest.glm is copied over into the test folder, as well as the 13glm. And then any other file that's stored in this GLM folder will be compared to outputs generated by the GLM file. So any differences or any missing outputs will be reported as errors, and the validation test will fail. So if we look at the, I must be missing a slide. I anticipated there'd be a slide here that would show the test output itself. My apologies, I'll have to fix that. So when we run the validate command, there are a number of options that we can use. There's a limit on how long a validation test is allowed to take on GitHub. That limit is right now set to 60 seconds. We don't expect any of the templates to take more than 60 seconds to run a validation test. If it turns out that this is not enough, we'll have to increase the limit to allow that validation test to complete. Otherwise, what will happen is it will report the timeout error on the validation test. This is critical because we have to be careful about validation tests that run away and essentially never complete. So that will prevent that situation from occurring. The other thing to keep in mind about the limit is that it's not available on Mac OS. The timeout command does not exist on Mac OS, and so that limit doesn't exist. It's not much of an issue, other than if you run your validation test and you don't pay attention to it, it might, keep running forever if there's a problem. The other thing is that if you want to see all of the commands that are being run, you can specify the verbose equals yes option on the make validate, and that will allow you to actually see all the outputs that are generated, all the commands that are generated and the corresponding outputs. So if you're running into a problem with the validation test as you develop it, this option is very helpful. So that's just a kind of a quick tour of how templates are validated. At this point, I'm ready for any questions that you might have before we'll do our pro tip and exercise. So if you have any questions, please feel free to ask them at this point. Okay, so what I'll do now, I'm sorry, I have a slide error. This is the slide I was looking for. There must be a slide sequence error, and I'll have to fix that. All right, so validation test template. So this is what the output folder looks like. So you'll notice that the test folder contains the original tree that corresponds to the template itself. So this is the integration capacity analysis template for California. The Autotest folder tree is simply a copy of the Autotest tree all the way down to the individual GLM file. You'll notice that the GLM here contains the original GLM file that we wanted to test. And you'll notice that the solar capacity file will be compared and checked. And if there's a difference, that will be reported as an error. So any error coming from the template will be output to the standard error, and any error coming from the simulation will be reported in the Gridlab-D.err file. So that's how the templates themselves output information. Okay, so what I wanted to cover next was a pro tip, and it's not uncommon for us to use Gridlab-D inside something like a Jupyter notebook or a scripting tool. And one of the key things that we do often is run a simulation, generate a CSV file, and then we need to load that CSV file using a module like Pandas. Now, when Gridlab-D outputs a CSV file, by default, it adds a whole bunch of comments in the CSV file telling you some stuff about the simulation and where that recorder was placed in the model and when that model was generated and what information is included in the data set. This is not convenient for a tool like Pandas. You can manage it, right? So here's an example of reading that comment header and extracting the column names and using the column names to essentially import the CSV file. Needless to say, it's not super convenient, but it does work. There is a way to make things a lot simpler. I alluded to it in the solution to the exercise for session 3, which is to set the CSV header type to name. And when you set the CSV header type to name, then the output of the CSV file is much more compatible with Pandas read CSV, because in this case, the only thing we need to tell Pandas is that the index column is the timestamp. Everything else is already done essentially in a way that Pandas can handle, and it can directly load the information. And notice that all the column names are set correctly. The index is correct. The only other thing we might want to do is tell it that the index column is actually a date stamp, so that we get parsing of the date stamp on that column. But otherwise, everything works very smoothly using this very simple solution. So this is a really helpful little feature. You will find that it's become increasingly common in HiPAS to set the header type to name rather than leaving it to the default, the legacy header type that was always used in Gridlab-D historically. So this is just one of these super helpful little tricks that I think is going to become so common at some point we may make the default value of this property the name, because that's almost always what everybody wants anyway. Okay, any questions about that before we wrap it up and talk about the exercise for next week? All right, so next week's exercise is to create a validation test for the filter directive when we use it as an integrator. Some of you may know that the discrete transfer function for an integrator is 1 over z minus 1. So that's how one defines it mathematically. And so this exercise is simply construct a validation test that creates a short time series that verifies that the integrator works in Gridlab-D itself. An implementation of GLM, defining an integrator and running that integrator will produce the result that is expected. So this kind of validation test is really common. It's used throughout Gridlab-D, where we make a particular feature do something in time, and then we verify that what it does is correct. So this will be we'll talk about the solution to this exercise next week when we dive into the modules and classes that are implemented throughout Gridlab-D. So with that, I think we are wrapping it up, unless anyone has any questions.